Boom. Done. You could still see my...
I am pixelated.
My crappy...
Now we're within very meta.
Is it like...
Yeah, but it looks kind of like a fold in space, Fraser, so it's okay.
Space time, yeah. Yeah. If I had any kind of like vertical surface behind me to hang, like I am this far away from the green screen, and the green screen is hanging over the bunk beds in the back of the trailer, which are filled with food and supplies and dirty laundry. And yeah, it is. I know it all looks so professional. Like
it's the glamorous life of a publisher, apparently.
Yeah. It's incredible. The sitting on my camp chair. I'm sitting on one of those canvas, those blue, those camp chairs that you fold out and sit beside the fire. And they
just got one for Christmas.
I had one of those in here for a while.
It's a very Canadian thing, I think. Like, I'm not sure if other countries use them, but we sure do in Canada.
Yeah.
And then the whole computer camera setup is set up on one of the bunk beds in the back of the trailer, and it's all sort of, so I've spread out over an entire...
You should do a tour at some point.
Yeah, no problem.
Yeah. We should get you a tent to produce from.
I'll just turn the camera around once.
Just rotate the camera.
Yeah, you'll get the gist of it. But we're like working on the shop. The builders are up working on the shop right now, and they just finished off the siding, and the electrical people are in roughing in all the electrics, right? And so just as a full-on comparison, like we've got like pot lights in the office, 9 lights on the ceiling, and then in front of my window, right in front of my desk, is the window, and around the window is going to be a dimmable, warmth changeable light strip that goes all the way around my window that I can just turn one switch and then I'm lit. The whole thing is lit, and then it's totally lit. And I've got four Ethernet ports right beside the desk that are just coming out of the wall that I can display, and I'm gonna network in the whole place with wired connection, so I'll have a nice wired route to the internet. And then there are 12 plugs on the wall within plugging range of my desk.
Nice.
Wow.
Yeah, because you never have enough plugs.
No.
Like ever.
No.
Ever. And so I'm just like, okay, so if I plugged in, I'll plug in my UPS, and then my UPS will have my computer plugged into it, and then I'll plug another thing over there and a monitor over there, and like right now, 12 plugs is about $5 more than one plug, right? When you're in the building stage and the electrician is just running outlets, and it's fine. It's absolutely no additional cost to do it. So yeah, I'm deeply looking forward to getting out of this trailer. And again, Like anyone who's like, oh yeah, trailer life, I love it. I wish I could live the trailer life. You do not.
Go along any highway and look at hotels, and there's always people with trailers parked there. That tells me that they don't necessarily like being in trailers all the time either.
Yeah, no, for sure. Like, like anytime we travel, like Carl and I travel, we did a trailer. We rented a camper in Australia, and that just confirmed for us that we never want to camp in a trailer or a motorhome or any of that, just because you're sort of packed in a crappy campground with a whole bunch of people in the city. Pretty much, it's loud. People are having parties and playing. Just stay in a hotel.
Tents the whole way.
Yeah, tent. So
Oh,
I like a tent in the forest, like way off the beaten track, or stay in a hotel or Airbnb.
Yeah, see, my idea of roughing it is a hotel with a black and white television. So it's not no more camping. No more camping for me.
Yeah, no, I I don't mind camping as long as it comes with a 10-kilometer hike first.
Airbnb. Morocco, we did all Airbnbs. I've never done a hotel in Morocco.
Oh, and I'm
our
sure
daughter went camping at 4 months. We were the only ones silly enough to be in the campsite in the cold season.
You're a maniac. We actually camped. Where did we camp?
She's now been to 3 national parks and camping more than amazing. Once.
Well, we did Yosemite.
Nice.
And it was nice. And we were in Sequoia. It was amazing.
Ooh, I love Sequoia. Yeah. I was in the redwoods on our trip up to Canada.
Yeah. So I don't mind car camping, but I definitely don't like being in a RV. Anyway, that's just me. I know I might be the there you go. The Canadian Space Advocate. I'm in a room with only 2 plugs. That is barbaric. That is uncivilized. Just remember, if you're going to have the electrician come by for any reason whatsoever, just have them add 10 more plugs.
Are you actively using your Starlink right now for internet? Or?
Yeah.
Okay.
Yeah. I mean, it's 40 Starlinks
looks
worse
like I should be.
than it was before. But,
but
we'll get
well, those never went online anyway.
That's Fraser, an excellent segue right there, Fraser.
Yeah. All right, well, let's get started. So just to let people know, we've got an interview that I pre-recorded. So we're going to go to about the 40-minute mark, and then we're going to just sort of sign off, and then Pamela is going to switch over to the interview, and we'll go from there. So I know it'll be reversed, but that's what makes the most sense. So here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, February 9th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Parker Solar Probe's photo of Venus, the youngest pair of asteroids ever seen. The Atlas Asteroid Telescope, fully operational. SpaceX lost 40 Starlinks. Planets, dead planets crashing into dead stars. And where did Jupiter's aurora come from? Joining me this week on my screen to my right, we got Beth Johnson. Hey, Beth.
Hello, Fraser.
I feel like it's been forever.
It kind of has been.
You've been busy. I think, so much work over on Daily Space and all this stuff. Pamela is like a...
Pamela is running a media empire now.
Yeah, I'm trying to. Yeah, media mogul. And as soon as you get close, you get sort of pulled into the vortex. And
I'm doing a lot more with SETI too. So it's the weight of the two things. So it's just been a lot of stuff going on.
Good. Well, we understand if you can't make it to the Weekly Space Hangout every week, but it's good to see you. We've got Dave Dickinson. Hey, Dave.
Hey. Still here
I only see one telescope.
Yeah, we moved the TV back out, so that means where the TV was, the telescopes are. So there's
really.
I've only got the Vionis one is so slim it fits right in there. I still have the other ones around.
So your partner just wasn't down with just sitting at the couch and just looking at the telescopes.
Well, we had the TV in the bedroom.
Entertainment.
Yeah, so every once in a while we get bored and put the TV back in the bedroom so we can just sit back there with it. So
yeah,
there's basically 2 slots to be in this entire place, the living room or the bedroom. So
yeah,
you're seeing about half the apartment right now.
Yeah, I don't think we'll put a TV in our living room. It's just like no point. Like we're gonna watch TV, watch in bed, and then if you're
Well, it's a catch-22. Then
outside,
then you're those people that fall asleep with the TV on full blast. So it's like,
I am for sure.
It's dangerous to have the TV in the bedroom too often.
Yeah, well, but my wife can't sleep in front of the television. Well, I sleep. I can't sleep with the television, so who knows?
Yeah.
And this is why you set it up to your smart device, and then you just tell that to turn it off.
Right. Or to like listen to you snore and then turn it off. We've got Dr. Nick Castle. Hey, Nick.
Hey, how's it going?
Good. Actually, Dave and Nick are like the 2 hardest working guys in the sci-fi. In the Weekly Space Hangout.
Doesn't that work the other way around, as we just covered with Beth? I mean, way to see you every week.
Yeah,
exactly. All right. Now, before we get into the news this week, and we do have an interview, but it's going to be at the end of the show, so just keep that in mind. But I want to give a huge shout out to our good friends, our fans, our executive producers at the Weekly Space Hangout crew. You can join this incredible community. They will give you news, friendship, camaraderie, and also all the executive control you would like to control who shows up to this show. You get to call the shot. So go to wshcrew.space and they will welcome you to this amazing community. All right, let's get into the news. Beth, go first. You've got 2 stories queued up. Pick whichever one you want, as long as it's about photos of Venus.
Sounds good. Okay, so photos of Venus. So there's this amazing mission out there called the Parker Solar Probe, which is basically designed to go do incredible science really close to the sun. And it sets records. It gets closer to the sun than any other mission. It goes faster than any other mission. It's amazing. And it sent back pictures of Venus that have got everybody sort of talking today, which is pretty cool. And it actually managed to, they say visible light, but let's call it the very edge of visible light. So it's like red into infrared, basically. Mm-hmm. And they captured images of what is the surface of Venus. So they actually have the outlines of continents and lighter structures, and it's pretty amazing to see it like this.
And Venus is a tricky place to observe. What does Parker Solar Probe have going for it that allowed it to pierce the smoggy atmosphere?
So it has an instrument called, and man, NASA and these names, it's called WHISPER. And it's basically wide infrared imaging. And so it can image between sort of that visible wavelength into near infrared. So 470 nanometers to 800 nanometers.
Okay.
And so what it's really kind of getting pictures of is heat, which is good because there's a lot of clouds on Mars. It's very hot and it's very difficult to see things in visible light waves. So this is as close as we get. And it's managing to sort of peer through the clouds to see the continental shapes at least.
Do you know
on the night side, this is not a day side image because you can't see anything. It's just blown out.
And that feels like a first.
Yeah.
Like I know that imaging Venus on the night side has actually been a fairly tricky job. And I know like the Japanese, like the Akatsuki spacecraft was able to do some measurements of the atmosphere on Venus's night side, but just in general, it's a tricky planet. Nick, you study planets.
Yeah.
I know it's not Mars. How do you feel about images of Venus?
I think Venus is pretty cool. Well, all right, technically it's really hot, but I try not to use that language.
Right.
It's a really interesting place. I mean, I'm a geochemist. I love looking at the rocks that make up these planets. And there's just a ton we don't really understand about the surface of Venus. Its volcanoes look different. The surface compositions and how they react with radar looks different from everywhere else we see. There's a wonderful debate over whether Venus has past evidence of plate tectonic, as in there's one plate that covers the whole planet, but still moves. or none of the above, like everywhere that's not Earth.
So we probably can't get any of those answers out of these pictures.
No, but every little piece of information we get, every other wavelength that we can peer through those clouds, we get a little more knowledge, which ties down our models and our lab experiments a little bit better and paves the way for understanding what's going on just that little bit more.
Beth, I got a question from Twitter when I posted a link to this story, and someone said, "Hey, isn't it supposed to be looking at the sun?"
Yeah. It's not so much. It is looking at the sun, but it has a big giant solar shield that protects it from the heat. And we actually interviewed the mission. I interviewed the mission scientist yesterday on Daily Space, and there was a
Nice.
whole conversation about how you have to design a solar shield for a mission that is literally coming within 9 solar radii of the surface of the sun, and then how you also have to have solar panels so that you can collect energy, but you can't have them aimed directly at the sun because then they overheat. And so it was a whole thing. But yeah, it's collecting some images, but it's mostly collecting a lot of sort of energetic particle data. So a lot of reading velocities and things like this as it figures out how things are speeding up in there.
But it's using Venus to get speed boosts. And so it happened to be passing overhead, so it might as well just take a quick look.
Yeah, speed boosts. And I'm not sure if it's definitely speed boosts, but I think there might be a little tiny bit where they're using it for drag as well, just depending on how they're trying to get in there. But they're getting closer and closer. They're coming up on their next close approach, February 25th. And I think that one's going to be at 11 solar radii. 13. It's really close. I mean, it's ridiculously close.
These Venus flybys are going to kick it out into a polar type orbit around the sun too, because that's the area they really can't cover.
There's 2 more Venus flybys left, and there's I think 3 years on this mission.
Well, they're going to stay in the ecliptic. They're not going to go polar. It's the solar orbiter that's
the ESA solar orbiter.
Yeah, solar orbiter's doing the polar. It's going to try to go polar. Right on. Cool. Awesome. All right, Dave, you're next. What do you got for us?
Let's do the one on Atlas first. Atlas is the Asteroid Terrestrial Impact Last Alert System, and this is a survey run by the University of Hawaii. It's NASA funded, and this looks for near-Earth asteroids, especially ones that are coming really close to us. And I hadn't realized that they were adding more telescopes to it until recently, until they released. Yeah, that's one of the sites down in. There's one in Chile, and there's one at Sutherland in South Africa. So they now have 4 telescopes because originally they had 2 up in Hawaii. And you see a lot of comets named Atlas, and you hear a lot about it whenever we have a near-Earth asteroid coming out. They found actually recently a couple that they saw right before impact, which is really when we want to see them, because previous to the Atlas survey, a lot of times we were hearing about near-Earth asteroids after they passed, or say in the example of Chelyabinsk, we're hearing about them the day they hit over Chelyabinsk. So that came at us actually from a sunward direction. So really the thing is we'd like to get better at seeing these small 20-meter, 30-meter space rocks and actually being able to identify them. So Atlas scans the entire night sky every night and produces a lot of data, of course. And now they have 4 telescopes online. So expect to see a lot more comets named Atlas very soon coming into.
It's incredible that they're scanning the whole night. It feels a bit like a precursor to the Vera Rubin Observatory, but with
and that's going to go even lower too. It's actually quite hard to see these really close asteroids. One problem they have that they addressed during the Litter survey a few years back was they're moving really fast too. So it's hard to catch them in many images as they're scanning the sky. So you need something that really can do these kind of wide, reflexively fast surveys, like fast all-field surveys. And they want to get out into space with like NEO Surveyor and things like that. Like I said, we have some blind spots like sunward coming at us, like Chelyabinsk did. I noticed that morning when I saw the angle, when we started watching the videos and we started kind of trying to piece together what exactly happened that morning. I was like, I bet that came at us from a sunward direction, and it did. That's why it managed to creep in and hit us without any warning. So
because it would be the kind of size that we should be able to detect, but we didn't know that it was coming.
Yeah, 20. Chelyabinsk was roughly 20 meters across, I believe it was. So it's something we should have seen. We really got lucky that day too, because it exploded over a city, I believe, 1.1 million. And there were some people injured, mostly from flying glass and things like that. But we were lucky that there wasn't anything worse. That if that had come in at a less oblique angle, that would have definitely been a bad day.
Yeah, the airburst was bad enough. I would not want that to come in at a steeper angle.
Yeah.
And so, any idea of like how much better protection this network gives us?
Well, like I said, we're seeing more discoveries even now. There's been a few already from the newer upgraded Atlas survey that I'm noticing when we're watching I'm looking at all the asteroid discoveries. We're starting to see them get out there before they pass rather than after they passed Earth. So that alone, I think, is kind of indicative that we're getting better at seeing these smaller rocks inbound before they. Like I said, it would be good if we could see more of them before. It was only a few years ago. It was the first time we saw one hours before it hit, and they actually managed. That was one hit in the Nubian Desert. I think it was 2008. I want to say it was 2008 TC8, TC3, something like that. They saw it about 20 hours prior, and they managed to actually. So they have a spectra of it, and they have the detection before when it was in space, and they actually got samples of it after it impacted. That was the first.
Amazing.
Was that the one they called Mbura Rockhole?
It might have been, yeah.
Yeah, sorry, I know the meteorite side of that, not so much the asteroid side.
Yeah, it took them. It took them a while, I know, to find. It was in the Nubian Desert in Sudan, I believe, that it hit. It took them a while.
Okay, then I'm talking about a different one, because I'm talking about one that they tracked into Australia.
This was Dr. Peter Yenniskins was one of the ones on the team, so I know about that. And his pictures of being out there.
Yeah, SETI does a lot of those.
Yeah, and you can see that being kind of an exciting possibility too, because there are several tons of space debris impacting the Earth every day, and so many of these leave fragments that are able to fall all the way down to the Earth, and those kinds of fragments are absolutely invaluable to researchers because you get a fresh meteorite, and so you could detect one of these inbound. Boom! It explodes in the atmosphere, and you could see that it's about to happen. Even track it happening, and then chase down where the meteorites. We had one in Canada that landed in a frozen lake, and
Tagish Lake.
Tagish Lake, yeah. And so the researchers were really excited because this was going to be completely preserved, and now it was a race to find it before the lake melted in the springtime.
I hadn't realized really till I read about there was a suborbital mission called SOFI that was looking at, it was a NASA mission at what they call meteor smoke, that actually meteors add to this load of high altitude dust in our atmosphere. And these add to like noctilucent clouds nucleate around it too and things like that. But it's interesting that when you mentioned how many tons of, it's like, oh yeah, I just wrote an article about that a few weeks ago that it's like that there's a constant rain of meteoritic dust that is coming down from, and you see actually meteor trains on large bolides and stuff. When you see fireballs, sometimes there's smoke trails that they leave for a time, but there's actually a layer of this that hangs out way in the upper exosphere of the Earth's atmosphere.
That's crazy.
It's also really interesting for geologists because if you get some of the orbital information before it hits, you can, and then recover the meteorite, you can start to trace that back to dynamical families and start to tease out, okay, which asteroids are these related to? How do we group these things? How do we make sense of the inventory of stuff in the solar system, without having to go out and grab it?
Well, spoiler alert, we're going to talk about that later on in the episode. So, all right, Nick, let's talk about a dead star eating some dead planets.
Yeah. So this has been a theory for a long time, 20 or 30 years. Sorry, for me, that's long. That at the death of planets, many of the planets fall into the atmospheres and ultimately get gobbled up by their stars. Particularly, this is interesting for white dwarfs, where something like a quarter to half of them have these so-called dirty spectra, where you a lot of heavier elements in the sun's photosphere. Now, we've only had a couple lines of not proof, but coincidental information that said this is probably what's happening. But just recently, a paper was published that said, now we finally actually observed the process. So what we'd seen before was these spectra that said these are heavier elements that should exist in the upper layers of a star. Heavier elements tend to sink towards the center of the star in plasma dynamics that make no sense to me because I'm not a physicist. But the idea is heavier things don't sit well in the upper layers of stars. They tend to sink. And yet we still see a bunch of these heavy elements there. So theoretically, they must be coming from somewhere else. They're not just staying in place. The other line of evidence was looking at debris fields around white dwarf stars and seeing, yeah, these match some of the spectral signatures we're seeing for elemental compositions in the star. But what we've just observed was X-ray emissions from this material actually breaking. So as it loses energy, as it falls down the potential well into the star, it has to emit that energy somehow. It comes out in the X-ray. And we used, I can never pronounce the name right, so the Chandra Observatory, the X-ray observatory in space, to measure the X-ray emissions around one of these stars and resolved that we're actually seeing this material emit photons in the X-ray spectrum as it's being absorbed into the sun's atmosphere. So that's finally okay, now we've nailed it. We know for sure that's what's happening. I thought that was a particularly cool article because I used to think about how planets come about, not, oh yeah, they got to die at some point. How's that going to work?
Right. So just to sort of understand this, then you had the star, it was a main sequence star. It had a bunch of planets around it.
Yep.
The star bloated up as a red giant, probably ate some of its planets, blew off a ton of mass, shrunk down to
all the way down to a white dwarf.
And then it still had some planets orbiting around it. How did they get in to get so close that they crashed into the star?
That's a really good question. I don't know. Anyone who's actually an astronomer want to chime in on that?
Yeah, I mean, I think just the mass loss causes them to turn into more of a debris ring around the white dwarf, and you get this material falling in. Like if you mulch the moon, if you've read 7Es, then the moon starts to rain down on the Earth because
smaller fragments are more susceptible to things like drag from solar wind. So if you've broken apart these planets, then you've got a better chance of dragging it into the center.
Yeah, and also just various interactions. But I wonder, like, if you lose all that mass, like I think a star will blow off like half its mass, more than half its mass in that red giant phase, and so that will suck those planets in because now the star has less mass. So I wonder, like, they'll huddle up closer, and so I just wonder, like, what are the interactions? But the point being that you could kind of guarantee that any white dwarf that you can see that has that debris in it once had planets.
That's an interesting thought. Yeah, this is evidence that this would have had a planetary system. We don't get to learn much about that planetary system.
Right.
But in terms of inventorying how many stars have planets, that'd be a pretty good indicator, yeah.
Yeah, like if you like measured the atmospheres of white dwarfs, now that you've got like this smoking gun that this debris equals debris, then suddenly you now have a way to study all of these white dwarfs that are out there. There was a survey that came out, it was announced like today, that they've done like 14, you probably saw this one, Beth. They've categorized the chemicals of like 14 million stars in the Milky Way, and they've published this online. So you can now go and look up the chemical fingerprint of 0.01% of the Milky Way.
I have not seen that, but I'm going to have to go hunt it down.
Yeah, it'll be in my Twitter stream. I think it was yesterday. It was released, and so it's. I mean, I love these ideas of surveys, like Gaia, Sloan Digital Sky Survey, what Vera Rubin is going to be doing. Just this ability to kind of go, I have a question, and then you go and you pull up all the data and go, aha, here's the answer, as opposed to having to take out any telescope time. So, so where do we know where we stand on this? Are we the planet that got consumed by the red giant, or will we be the planet that gets smashed up and absorbed by the white dwarf later on?
Well, I got to admit, the article I read didn't go into that one. I think the morbid fascination of what might happen to the rock we're standing on in about 4 billion years just wasn't on their horizon.
It's never too.
But from what I understand, we're
think about it. Yeah.
Yeah. Is the Earth cremated or otherwise cremated? It's going to be one of the two.
Yeah. It's they actually go back and forth all the time. So
yeah, I've seen some people say that the boundary will hit Earth, and some say it'll like almost reach Mars, and some say it'll barely hit Earth. It might not come quite close. No one knows.
We need to know if we're going to be a planetary nebula or not, so I can up my Star Party spiel. Right. There's always the controversy about. We always like to say that planet, like the Ring Nebula, our solar system will look like that someday. But I know we've written articles before where they've cast doubt on that before.
Yeah, so. This matters.
Yeah,
this matters. Whether or not the Earth survives the sun turning into a red giant, this is important. This is where I keep all my stuff. So, all right, Beth. We spoiled your story. Let's
a little bit, but it's okay. So you brought up surveys, and one of the surveys that I am a fan of is Pan-STARRS. Pan-STARRS, again, is another one of those surveys out of Hawaii that is looking and finds comets and asteroids all the time. And they found this pair of asteroids, 2019 PR2 and 2019 QRS, which are, so they're tiny. So the largest one is a kilometer. That's the big one. And they're a pair, and they're apparently only about, the parent body split them off about 300 years ago. So they're the youngest asteroid pair that we've discovered so far. Not that they're young as far as rocks go, but they are a young pairing. So they not only did they find this in the current surveys, but again, as you said, you can go back into some of these other surveys and go through and find what we call pre-covery data and confirm it and get more information on the objects that you're looking at. So they went into the Catalina Sky Survey and basically found that 14 years worth of data that they could actually sit there and go through, and that leads them back to where it comes from, where their orbits were. And as Nick said, you can kind of track that back to sort of the origin and that kind of thing. There's a possibility it's a comet that split apart, but there's no signs of any cometary activity, so they can't confirm that. Still, it's pretty neat.
Yeah, I guess if you go back to Galileo's original observations of this object, it would have been a single asteroid.
Yeah.
When he was observing the the planets and the moon and such.
Man, I better email him for the digital records.
Yeah, exactly. Yeah, you want to study his old drawings of the asteroid.
You probably saw, Fraser, that you probably saw that Galileo did sketch Neptune when it was near Jupiter. This was only found like in the 1970s or so. He sketched it as a star, and he actually noticed that it moved, but he didn't identify it as a planet. And they found this, I think it was in the 1970s or so, and they sleuthed it back, and they were like, yeah, Jupiter and Neptune were in conjunction that night. Neptune was very nearby. He actually sketched it in his notebook. So he could have potentially discovered Neptune in 1610. That would have been, but they didn't have any idea. They didn't have any idea there should be any more planets out there. So they weren't really looking for them. Yeah,
the church would have loved that.
Yeah.
Yeah. That's awesome. Fantastic. And so, I mean, they're not dangerous. They're just trucking along.
They are near Earth asteroids, so they do fall into that category. But they're not. We are not being threatened by anything that we've seen so far. So for at least, I think it's like 115 years.
As long as they keep their distance, we're going to be okay.
Exactly.
Fantastic. All right.
But remember, everybody, do keep looking up.
Yeah. They could split off again. This is like a real life game of asteroids. could there be a little spaceship out there shooting apart these two rocks? I think this
Yes,
is
but it hasn't
evidence.
fired its shot yet. It's called DART.
Yeah.
That's coming right up this year.
Yeah, I feel like this is evidence of extraterrestrials playing a game of asteroids in real life. That asteroids is actually a
Yeah, don't even
historical
start.
record of a battle the aliens fought 400 years ago against a space rock. I'm just putting that out there. I think we need to explore this idea.
Duly noted, Fraser. Duly
All
noted.
right. Okay. All right. All right, Dave. You're telling me that I might have a problem with my Starlink?
I doubt it's going to affect your Starlink, actually, but we did have an interesting mystery this past weekend that SpaceX finally had an announcement and solved. They did a Starlink launch, which are becoming pretty routine. They've really had a breakneck pace with deploying these satellites. Once every couple weeks, there's been a Starlink launch. And they did one out of the Cape Thursday. And when Space Track, when NORAD published the first orbital elements, a bunch of us online that are always looking at these to do our first sighting opportunities as these Starlink trains go around the world, noticed that they only published a partial batch for elements. And when we plugged them in and looked at the perigees were really low. I mean, like re-entry kind of low. We started discussing this online. Me and a bunch of other satellite trackers were like, I don't think those are going to stay up very long. SpaceX was kind of quiet about it. And then last night they dropped an announcement saying that, yes, there was a solar storm Friday, shortly after they deployed these. I don't know if this video will work well. This is another mystery we had on the 7th, that there was a re-entry over Puerto Rico. And all of us that are watching and trying to identify what these re-entries were couldn't really place us on a satellite. But then we started noticing the orbital path was very suspiciously like the same inclination. It was Marco Langbroek was looking at the orbital inclination on this re-entry. This is from the meteor cameras of the Southern Astronomical Club in Puerto Rico. Matter of fact, they caught this. And they started noticing that this looks a lot like one of those Starlinks potentially on its orbital trail. And so SpaceX announced yesterday that, yes, there had been a solar storm. Now, when you have solar activity, that puffs the atmosphere out, of course, and it speeds up a lot of re-entries. And we have a lot more, like, as we're going into, the sun is more active right now with solar cycle 25. They just had the bad luck that when they did their deployment, a lot of these satellites got knocked out, and they're saying about 40 of them are probably a loss over the next few weeks are going to be coming back in, out of 48, I believe. So, but of course, there's like 1,700 Starlinks up right now. So,
but they have like they have to go into some kind of configuration, like as they're raising their altitude.
Yes,
they have to go into a configuration that essentially puts them edge on to the Earth's atmosphere to minimize the drag, and they couldn't send the commands because they were all, bzzzt from
they were edge on
the solar storm.
Yeah, but they didn't get that key command for because that's usually when they're the most visible, is before they do this raising maneuver to get them up into a higher altitude. That's when everybody starts seeing Starlink trains, is right after they're deployed, is the key time. Then they get they go below naked eye visibility now once they're up at higher altitudes. But this is the first batch that they put up that is probably a loss. And they're actually replacing a lot of the older Starlinks now. They've been up that long that a lot of the older ones have been re-entering anyway. There's a few re-entering every week, but there's definitely going to be a lot more re-entries over the next few weeks from this launch alone. So
yeah, this sucks.
Yeah.
The timing. I mean, we've known that these geomagnetic storms are an issue for satellites and for the electrical grid down here on Earth. But as there are more and more satellites, this is going to become a bigger and bigger issue. And, losing a satellite also means losing your ability to tell it to avoid other debris, to dodge other threats, to not hit the International Space Station, etc. And so you can kind of envision, as worse solar storms happen, and
we had the Russian ASAT test last year too. That added a lot more debris to low Earth orbit.
Yeah.
So, and we've got another constellation that's been going up, OneWeb. Matter of fact, they're launching their 13th batch of satellites tomorrow. So, and I managed to get actually a reply from them on Twitter that they're going to be going online later this year, they're going to start providing internet service through OneWeb. So there's going to be a lot of other alternatives out there pretty soon.
Did you hear about this satellite that has been communicating with people's smartphones and Internet of Thing devices? So they've launched a satellite that's sort of a test, and they were able to they flew it overhead. Essentially, it can communicate with a smartphone because it's directly overhead, and they flew over the Bahamas, I think, was where they had set up their whole test facility, and so someone was able to send and receive messages to and from another user just using their smartphone, using essentially a Wi-Fi connection to the satellite.
Look that up. No.
Yeah, and so just a couple of days ago, it was on Space News. If you go to Space News, they've got a story about it. I was going to try and research into the original. It's Links.
Well, that's probably the next step, though.
Yeah, Links Communication. So it's round 2. They had the satellite just randomly connecting to every single device that it could get its hands on as it was flying overhead. Anyone with an open connection is essentially anyone looking to connect with open Wi-Fi. It was going, I'm open Wi-Fi. And so they said they got thousands of connections out of this satellite.
That's fascinating, a bit scary too. That's like a year or two ago, there was a casino that their mainframe got hacked through the thermometer in one of their aquariums was hooked up to the Internet of Things, and that's
right.
how they got into the system.
Yeah. So but you can just kind of imagine this time when just your regular smartphone will give you really crappy internet service anywhere on Earth.
That's probably where I'll get into Starlink, when I can there's a pull down menu on my phone and it says Starlink and I can just hook onto it.
Yeah. I promise you, when you're not able to get a fast connection, that's when you'll go for Starlink.
Yeah.
There was no way I could get internet where I am, and the regular satellite internet is terrible. All right, Nick, one last story, and you got to do a quick version of it. Jupiter's auroras come from what?
Comes from Io. So there's a new study using data from the Juno spacecraft that was looking at the dawn-side aurora. And they were finally able to pin down a very strong correlation between what was going on in Jupiter's electric fields, which is what's charging the particles coming off of Io, and the occurrence of Jupiter's aurora. So this was finally pinning that last little link to say, we've suspected this for a long time. We've argued about this a lot. This is the nail in the coffin. We know for darn sure this is absolutely what's happening.
Very cool.
I love my little moon. I love my little moon.
Io is so your little moon?
Yeah, Io's my baby. I love that one. That's my favorite.
Most volcanically active object in the solar system.
You must be sad that the mission was canceled to Io.
I was. I'm really happy for the Venus missions, but I was really sad about not getting the Io one.
Would you have picked Io and Triton versus 2 Venus missions?
Yeah, I would. Honestly, I would. I think Triton is incredibly fascinating too, and we don't know nearly enough about it.
We've seen,
I understand.
We've seen Venus, and anyway, I'm just going to push Venus into the sun anyway. So
it would just take forever to get to Triton, though.
It doesn't matter,
decades.
Right? You can learn a bunch of mysteries about Venus, but it's too late because I have already gone supervillain and pushed it into the sun. It makes
that's what's really going on up there at that trailer.
It makes the stability of the rest of the planets better. So just something to think about. Anyway, was there anything else that you thought you should add to that, Nick, or should we shift to to wrapping this up?
No, I'm good.
Okay, all right. Yeah,
I'll keep it nice and short since I'm playing astronomer this week.
Yeah. How does it feel? Next week, astrophysicist.
I just got to say Mars a lot of times to make myself feel better after the show.
Yeah, you didn't get a chance to say Mars once, so.
Well, now I have.
Perfect. All right. So just another reminder, stick around. We're going to do an interview, a pre-recorded interview that I did about that story about the local bubble a couple of weeks back. And it's a fascinating conversation. You're really going to enjoy it. But it's going to be completely automated from this point forward. So the guests, the co-hosts and I are going to leave, and the interview will continue to play. So, Beth, what are you working on, and where can people find out more about you?
As always, I'm working on Daily Space. We're taping 2 episodes tomorrow, 1 on Friday, and I will be hosting SETI Live next week to talk about some CAMS work, the Camera for All Sky Meteor Surveillance, or that's on the 24th. So that's coming up, and talking to some undergrads who are actually getting to work on that program.
Fantastic. Dave.
Frequent contributor, Universe Today, Sky and Telescope, author of Universe Today, Guide to the Cosmos. I think I got the book up over here. And the new Deep Sky Field Guide, well, new being it's been out for a couple of years. And working on the satellite tracking guide, I think is the third book I want to do, either
awesome.
through a publisher, or I'll publish it myself if I have to, but Kickstarter it or something. But
yeah, I can help you out with that if we need to. But awesome. All right, Nick.
I am the wandering scientist. I'm actually working on trying to get that going a little bit better. Something about I've already been wondering, maybe I should finish blogging about it. Also trying to find more ways to say Mars
about
in daily
life. Did
you
even go there?
Hey, look, I've got the pics. I know it happened.
All right. But how will we know? It's like a tree falling in the forest.
WanderingSci.com.
There you go. Awesome. All right. Thank you, everyone, for joining us this week. And remember to stick around. This is not me saying goodbye. This is just me saying goodbye. Here is the interview. Enjoy. Thanks for everyone for hanging out with us. Thanks everyone on Twitch, YouTube. Thanks to my co-hosts. Thanks for a special guest who's right over there in a second. And thanks to Pamela, who is engineering behind the scenes and is figuring out how to make an interview work during the live show, recorded interview. So I look forward to seeing how this works out. Thanks, everyone, and we'll see you next week. But don't leave, because now there's an interview. Recording. All right, so joining us today, we've got Michael Foley. Michael, who are you? What do you do?
Hey, great to be here, Fraser. So I'm a grad student at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. And I'm advised by Alyssa Goodman and Lars Hernquist. And working with Alyssa and other members of our team, we've recently put out a paper about the new information we found about the local bubble and a frontier of star formation that basically it created near us. So my research is about stellar feedback and how it relates to further star formation. So this is kind of right on my alley. So I'm excited to talk about it.
And this was a very big piece of news, probably the biggest piece of news that came out of the American Astronomical Society meeting. I know it was definitely one that we all jumped on and covered. Why do you think this was such a sort of big piece of news for astronomers?
I think it's so exciting because, we sit right within the local bubble. We have a front row seat to all of this, and we've known about the local bubble, its existence as sort of this big void of hot gas surrounding our sun, a couple hundred parsecs in diameter for decades now. What we haven't known, though, is the relationship between the local bubble and star formation nearby. So using the power of 3D dust mapping, we've been able to, for the first time, visualize the local bubble in 3D and connect it to these local star forming regions. And we found that basically all of the local star formation, local meaning within a couple hundred parsecs of the sun, falls on the surface of the local bubble. So it's kind of an origin story for these stars. As the local bubble expanded, it swept up gas and really kind of triggered a lot of the star formation we see today.
And how unusual is the local bubble to find this? Even like, how would you define it? Like, as a region of lower density pressure, how would you describe what the local bubble really is?
Right. So it's a giant void sort of hot gas. We think these super bubbles are actually pretty ubiquitous throughout the galaxy. Even going back to like the Copernican principle that the sun can't be any sort of
right.
A privileged place in the galaxy. Just by the fact we fall within the center of this seems to suggest that these are not all that uncommon. And then on the edge of the local bubble, now we've been able to actually map out the dust, which we can use as sort of a tracer for some of the gas as well. But we think about 1 million solar masses of material lies on the shell of this local bubble. So as about 14 million years ago, we think supernova started going off that have continued on till almost present day that have been powering the expansion of the local bubble. As it expanded, it swept up material. We're left with then a dense shell on the outside, which is composing a lot of these star forming regions, and then just hot, sort of low density gas on the inside.
Right. And and I remember sort of in the image, you could see that there are, and actually your background sort of shows it, that there are these star clusters that are forming around the outer reaches of the local bubble. So is that kind of like what the effect of this is as this sort of bubble moves outward, it compresses gas and begins these new waves of shockwave? And is it a chain reaction?
We think so. That we think this is a story of stellar death prompting new stellar birth. People have hypothesized this mechanism of star formation known as triggered star formation for quite some time. People have studied it a lot in simulations and stuff. We think this is the closest and best example of that happening, where we have continued stellar death in the form of supernovae, pushing out an expanding shell. As the shell expands, eventually the density in the shell will be such that you can induce gravitational collapse and start forming new stars. So in essence, as the supernova go off, it's triggering new stellar birth.
And 14 million years is not very long in galactic time. And would you imagine that this, we talked about this idea of it triggering. So is this bubble just kind of moving along in the Milky Way, finding new pockets of gas, compressing them down, generating new young stars, they're exploding supernova, creating more of a shock front that's finding its way to other sort of primeval gas and continuing this process?
Yeah, as you know, 14 million years is not long at all on a galactic timescale. So we do think that this is a pretty transient structure. We don't view it as something that will, persist through many galactic rotations. And actually, the sun itself only entered the local bubble about 5 million years ago. So the fact that we fall right in the center is purely by coincidence. So we think that
the fact that we have this bubble that is giant, perfectly surrounding the sun, I can see why that definitely makes your Copernican sort of hair stand on end, because this, we shouldn't be special. Why are we in the middle of this giant bubble of gas? It's a little unsettling.
Exactly. And it almost seems too good to be true that we're right in the center. So it was definitely the cause for a lot of skepticism in our group meetings when we were like, sun's right in the center, that can't be.
But coincidences are inevitable, right? The sun and the moon are the same size in the sky, and that's pretty weird, and had to see that at perfectly the right time in sort of astronomical history. So what story do you think this tells us about the formation of the sun and other stars within the local bubble, or just star forming in general?
So we think, as you mentioned with the Copernican principle, we think that, it means that star formation might occur more frequently as the result of these bubbles and supernovae than previously thought. So the fact that we're right in the center, seems to suggest that they might not be all that uncommon. And then when this is coupled with the discovery of the Radcliffe wave, which is sort of almost a 3 kiloparsec long structure of undulating gas that houses a lot of other nearby star formation, we think that, we're going to start discovering the 3D structures that are governing a lot of star formation, that star formation isn't necessarily happening in isolation, that you might require some of these larger structures to induce star formation, whether it's some sort of undulation that's happening with the Radcliffe wave, the physical mechanism there remains unclear, or supernovae powering something like the local bubble.
And I know this has been a bit of a controversy, that in the olden days, the assumption was fairly clear that you had these large clouds of cold gas, that something would begin their process of collapsing, maybe a supernova, maybe a star passing too close, whatever. What do you think is kind of the most modern take on this idea? What is the kick that triggers star formation? Is it more complex than we used to think? It has to be, right?
Yeah, so that's a great question, and I think that there's a lot of different ways to approach it. I've tried to approach it from the idea of a shockwave passing through turbulent gas. So a lot of my research is trying to study the structures that occur just behind that shockwave, because then you're going to deal with gas that has, been reached an elevated density, and it's sort of shielded a little bit from the turbulence by the shockwave that just passed through. So the suggestion there is that the gas just behind a shockwave may form a lot of the seeds for star formation. So I'm interested in exploring that more. I think the local bubble provides an excellent laboratory to test that theory, because we do see an expanding shockwave that is triggering a lot of star formation. But I'm excited to see what will happen as we continue with the 3D dust mapping out a bit farther. I think, we have the local bubble, we have the Radcliffe wave, but once we start going out to kiloparsec scales, and understanding that in 3D, that'll really give us the clues to what's going on with star formation.
And what does that future hold? Do you see the local bubble kind of petering out and eventually just switching back to the background density of the rest of the Milky Way, or will it continue this trigger of star formation? We talked about it maybe chain reacting, but even just the bubble itself, will it eventually run out of juice?
Yeah, we think so. It's already reaching. So right now, it's still expanding at a velocity of around 7 kilometers a second. So it's starting
slow when I sort of think about sort of speed in space.
Exactly. Yeah. No, it's not a fast moving thing by now, and it's reaching sort of the ambient turbulent velocity of the ISM. So pretty soon we believe that this will just sort of merge with the background, dissociate, and then the new star formation that it has prompted might create a new super bubble that takes its place. And so
I'm sort of imagining, like, if it is all down to 7 kilometers a second, which sounds fast, but the Earth is going 30 kilometers a second. Spacecraft, the International Space Station is flying at about 7 kilometers per second overhead. So
exactly, yeah.
It's not that fast. But if we roll the clock backwards, like, these are driven by supernovae, so the speeds must have just been ridiculous early on as these supernovae were detonating.
Absolutely. I mean, if I'm remembering correctly, I believe that, just after a supernova goes off, you're dealing with speeds tens of thousands of kilometers a second. Yeah. So it's a testament to how much material this bubble had to sweep up that it was able to be slowed down so much by the ambient ISM. When you're having. Yeah.
It's really interesting, because sort of I'm envisioning like if you had, say, another supernova go off in the void, in the bubble, it would have less friction and perhaps could have a wider impact. But if you had a place that was already quite dense with the ISM, with the interstellar medium, then maybe the supernova would be slower. So it sounds like there's a lot of factors that come into play that just define how all of these pieces fit together.
Yeah, that's an excellent point, and one that's just being started to explore a little bit more in simulations. So there's this idea of like a momentum boost if a supernova goes off in a somewhat empty region versus just going off in a dense region. You can change the amount of momentum that supernova is really giving back to the ISM based on its surroundings.
And this may be a little sort of outside of your scope, but one of the big mysteries is the population 3 stars, the ones that formed right at the beginning, the first stars, where you didn't have previous stars to cause overdensities, underdensities, etc. Do you think that any of this research can help us get a sense of what happened at the beginning of the universe?
So that's a great question. And yeah, it's a little bit outside my expertise, but I do think that, it can provide clues for the earlier stages of galaxy formation. I think, there's, I mean, this idea of triggered star formation, I do think would be relevant throughout timescales. But that being said, I'm not too sure exactly what we can extrapolate to the POP3.
And then I also think about, like, the party's pretty much over in terms of star formation. We're only getting a couple of stars a year forming within the Milky Way. But if you go back to, say, 3-4 billion years after the Big Bang, it was vastly different. So how do you think those dynamics played out differently early on in the universe?
Absolutely, yeah. If you're dealing with a lot of star formation, then you're going to get a galaxy that looks a little bit more like Swiss cheese, where it's just bubbles everywhere when you have rapidly producing supernova. And so it'll be interesting to see how this idea of triggered star formation plays into the formation of structures like spiral arms.
Yeah.
One thing we're exploring now is if the Radcliffe wave, which we believe is a section of the local arm of the galaxy, could have been formed by some of the interaction with the local bubble.
Right. And sorry, you used this term I wasn't familiar with it, the Radcliffe wave.
Oh yeah, sorry. So that was a structure discovered by João Alves and a lot of the members of the team who contributed to the local bubble work, and it centered on this idea of 3D dust mapping too. So when we were able to place a lot of the local star forming regions into a 3D context, including some of the ones that fall on the shell of the local bubble, they found that over about 3 kiloparsecs, star formation proceeded in a remarkably straight line. And then it had a bit of a waviness to it too. It looked kind of like a damped sine wave. So we think that the local arm of the galaxy isn't just like this flat thing in the galactic plane. We think it's actually kind of a wave.
Right. And like I know like the spiral arms of the galaxy, they're not actually arms, they're just a density wave that's moving through the galaxy, regions of higher and lower density, but different stars at different times. As these spiral arms sweep by, do they have an impact on the formation of these bubbles and the density of them and all that?
So that's a great question. In some simulations, it does seem like the formation of bubbles might be impacted by a spiral arm sweeping through, just because if you're forming a lot of stars in these spiral arms, the stars might either end up leading or lagging the spiral arm, and then exploding and even assisting in more formation in the spiral arm, because then the exploded gas then re-impacts the spiral arm and triggers further star formation. So in simulations, I'm thinking particularly those done by like Eve Ostreicher and her great group at Princeton, they do see an impact of that.
And so what's next? What is the future of your research to try and get a better sense of this?
So one question we're really interested in studying a bit more right now is the impact of the local bubble on the Radcliffe wave. So we've been able to place all star formation basically within 500 parsecs of the sun into one of these two structures, the Radcliffe wave or the local bubble. And then we found another sort of long straight structure. I said we found, that's not totally accurate. That's been discovered before, but we're putting it into sort of a 3D context.
Yep.
So we're interested in seeing how these three structures, this long split, the Radcliffe wave, and the local bubble interact. And using kinematics from Gaia and then 3D dust mapping, we can start telling the story of how all three of them evolved together. And so I think that'll be interesting to explore more.
And James Webb is sort of a perfect machine for peering through gas and dust thanks to the infrared. Is there any connection, any plans to try and get some time on James Webb to further this research?
We would love to. And actually, the software that's been used for a lot of this research, the glue visualization software, has been pegged as one of the visualization softwares that James Webb would like to use a little bit more. So
okay.
We're hoping that the visualization tools that have been used for this research will be useful not only to us, but to any researchers who are getting data back from James Webb.
It's interesting. We have this joke here on the channel that it's always dust. That right, no matter what it is that you think you've discovered, but in this case, you're looking for dust. So I think it's you would be anything but thrilled, to find dust. Well, Michael, thank you so much for taking the time to chat with us today. Super interesting. Congratulations on the research so far, and I look forward to seeing what comes next.
thank you so much for having me. This was
All right.
great.
All right. Take care.
Thank you. You too.